All right, let's talk about Newton's universal law of gravitation. I like to abbreviate this by NULG, just easier to keep up and say. Until now, we've used one expression to talk about the gravitational force on an object due to some other really large object like Earth. We've really only talked about the gravitational force of things on the surface of the Earth due to the Earth. We found the equation F sub g is equal to m times g, where that value g is 9.8 newtons per kilogram. You know that we often use 10 newtons per kilogram to make it a little bit easier. But whether we use 9.8 or 10, the idea is it's a constant value near the surface of the Earth. You should remember that forces have to contain two agents, one that the force acts on and the other that the force acts by. As an example, consider a book on a table. We can say that the normal force is the force on the book by the table. Note I have the on part and the by part. We can also talk about the gravitational force as being the force on the book by the Earth. So like in any force, the gravitational force has to involve two objects. But there's a more general expression for gravitational force. Newton was the first one to discover this and mathematically model this force. Newton was a genius. This is arguably one of the greatest things that humans have ever discovered. No one really knows if the story is true, but it really makes a good story. Think about Newton sitting in London, outside in his garden. He gazes up in the sky and sees the moon. One can see the moon even in the daytime because it is so close by. And looking at the moon, an apple falls on it from a tree over his head and hits him on the head. In that moment of insight, Newton realized that the force that caused the apple to fall to the ground towards the center of the Earth and the force that keeps the moon moving around the Earth in uniform circular motion, where the acceleration is towards the center of the Earth, were the same force. Let's look at some numbers. Consider the apple's acceleration down to the ground. We know that that's a constant, about 9.8 newtons per or meters per second squared. Now consider the moon. Scientists in Newton's time knew how far the moon was away. It's 3.844 times 10 to the 8th meters away. They also knew that it took about 27.3 days to go around the Earth. That corresponds to about 2.36 times 10 to the 6 seconds. Here I converted distances and times into the normal meters and seconds. So we can calculate the acceleration of the moon around the Earth using the expression 4 pi squared r over t squared. We talked about that earlier. If you put the numbers in, that comes out to 0.00272 meters per second squared. Now, to look at it at first part, the 9.8 and the 0.00272 really seem to have nothing in common. But if we take a ratio of these two numbers, the 9.8 divided by 0.00272, we get about 3,600. So what? What's so important about that? Well, if we look at the ratio between the radius of the Earth, that would be the distance from the center of the Earth to the surface, and then the distance from the center of the Earth to the center of the moon, we find that that ratio turns out to be about 60.3. Coincidentally, 60 squared is close to 3,600. See the comparison between the two numbers. So Newton was able to take those ratios and notice that the acceleration had to be equal to the square of the ratio of the distances. Newton concluded then that the gravitational force was directly related to the masses and inversely related to the square of the distances. That's a lot of math and a lot of derivations, but it is really considered one of the greatest scientific achievements of modern science. In fact, in order for Newton to prove that all the mass of the Earth and all the mass of the moon could be concentrated at its centers, he had to invent integral calculus. So next time you're in calculus class, you can thank Newton for what you have to do. There's even more to this story, but we'll talk about that in a bit. So here's the generalized equation for the gravitational force between two objects. F sub g is equal to big G, m sub 1, m sub 2 over r squared. So it's directly proportional to the product of the masses, that's the m1 times m2, and inversely proportional to the square of the distance, that's the 1 over r squared. 1 over r squared forces and 1 over r squared relations are very, very important in physics, and we'll run into them all the time. It seems to be a basic makeup of our universe that most forces and other such phenomenon obey this 1 over r squared dependence. G is a constant of nature. It was discovered in 1799 by Henry Cavendish doing a very elaborate experiment. It's 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared. It's a really small number. It's kind of a mystery why it's so small. M sub 1 and M sub 2 are the masses of the two objects in kilograms. And then finally, the R doesn't stand for a radius. It stands for the distances between the centers of the two masses. If the objects are really small, then we don't have to worry about their size. But if the objects do have size and shape, we need to know or to estimate where their centers are in order to find the distance between their centers. In the Earth-Moon example that we just were talking about, the Moon is about 60 times further from the center of the Earth as the surface of the Earth is from its center. So let's look at this expression for the gravitational force and the other expression we used. At the surface of the Earth, each expression must give the same values. So mg, the expression we've used before, must equal g, but now we have to put in the two different masses. One of the masses involved is the mass of the Earth. The other mass is the mass of the object we're concerned with. Well, what's the distance now? The distance isn't zero, because we have to talk about the distance between where the object is located and the center of the Earth. That would equal the radius of the Earth. So I replace one of the m's with m sub e and the r with r sub e squared. So an object of mass m on the surface of the Earth is the radius of the Earth away from the center. So that that's the r we're going to use. Similarly, the other mass, as I said, is the mass of the Earth. We find that g can be determined from big G, m sub e, and r sub e. Put the values into your calculator, noticing that the masses are going to cancel out, and you should be able to calculate the value of g. It just depends upon the physical characteristics of planet Earth. If I put the values in, not surprisingly or surprisingly, you get 9.81 newtons per kilogram. That number we've been using, the 9.8 or the 10 newtons per kilogram, isn't just a made-up number. It comes from the physical makeup of the size and shape of the Earth. It's very cool. Historically, we did not know either g or the mass of the Earth until 1799 when Cavendish was able to experimentally determine g. Then it became simple math to calculate the mass of the Earth to be 5.98 times 10 to the 24th kilograms. That's a really big number, and it's one of the first really big numbers that humans calculated using the modern science of Newton. Let's try some examples. First, here's an example involving typical size objects. Consider two high school students, one of mass 65 kilograms and the other of mass 45 kilograms. They're separated by a distance of about 2 meters. That's typically two teenagers standing in the hall talking to each other. What is the gravitational force between the two? If I put the numbers in, 6.67 times 10 to the minus 11th times 65 times 45 over 2 squared, I get a value of 4.88 times 10 to the minus 8th newtons. That's a really small number. It really isn't even measurable by most equipment we have today. And when you think about the other forces acting on a teenager while you're standing in the hall, like the normal force, or the gravitational force due to Earth, or the frictional force, you really don't have to worry about it. It's just so small it doesn't matter. In fact, the gravitational force is really only important if you're located near a planetary-sized object like Earth. Because Earth is so big, it does exert a measurable force on objects near its surface. You know, we call that the weight. But you are stronger than the Earth's gravitational force, believe it or not. Just pick up a book off the table. You are exerting more force on the book when you lift it up than all of Earth's mass does on the book trying to pull it back down. Now, let's find the gravitational force between the Earth and the Sun. The mass of the Earth is 5.98 times 10 to the 24th kilograms. Mass of the Sun, 2.00 times 10 to the 30th kilograms. And then the radius, or the distance between the Earth and the Sun, is 1.5 times 10 to the 11th meters. If I put all those numbers into the NULG equation, I get a value of 3.35 times 10 to the 22nd newtons. That's a big number, but it does involve stars and planets, which are also really big. Gravity is really only important on the planetary scale unless you happen to live on a planet. Because we live so near or right on a big planetary mass like Earth, gravity does become important. NULG, along with Newton's laws, allow all of us humans to accurately and predictably calculate things like planetary orbits. You're really doing rocket science when you use these equations. Just a note, we now know that NULG is not correct. It's just an approximation. A better description of gravity and how masses are affected by it come from Einstein's theory of relativity. But as long as we're not moving really fast, like close to the speed of light, or we're not living near a black hole, NULG works fine. We can combine Newton's laws and NULG to explain the motion of planets. These rules were first empirically discovered by Johann Kepler. We'll talk about Kepler's laws in another video.